Hey, welcome back. So in this section, we're talking about search and searching algorithms. Now, when I say search, some of you might think of something like Google right away. Now, the algorithm behind Google and its search is very complex, probably one of the most complicated algorithms out there, and it's probably more like 10 different algorithms that are being tested at any given time and things that are being tweaked. Not to mention the fact that this algorithm changes so much depending on who you are, your browsing history, the things that you've done, and the things you've clicked on. So when I search for Howler Monkey, I might see different results than if you search for Howler Monkey. So we're not going to even try and recreate anything like this. What we will get to later in the course, not right now, but later once we cover graphs and trees and other complicated data structures, we'll discuss how to search and traverse something like a graph, which is closer to what Google is doing. We're not going to talk about the machine learning behind all of this and how it decides, what is best tailored to me, Colt, versus to someone else down the street. We're just going to talk about when Google first started, before it even cared about people and ads and tracking all of that. If there even was a period, who knows? I doubt there was. But if there was, then we're going to kind of approximate that. But for now, what we're focusing on are even simpler searching algorithms that are really commonly used, but we may not often call it search. For example, let's say that we have a string and we're checking to see if there's another string contained in that string. Or let's say that I have a website and I allow people to sign up and they add their username in. So they sign up with a username and password. Well, we need to tell them if their username is taken. So let's say there's not even a database. Let's not worry about how this works. But let's say I have an array of usernames. If somebody types in a username into the form and says, okay, I'm going to be I hate cats. That's going to be my username, and my password will be secretly loves cats 72 or something. If I hit enter, the developer, needs to take that username and somehow figure out if it's taken. So if I have a list of usernames, how am I going to figure out if this I hate cats is contained in that list? Now, JavaScript has many built-in ways of doing this. You could, for example, do index of. It's a simple one. And here, let's try that. Usernames.index of I hate cats. This is using a searching algorithm behind the scenes. And so we get 11. And if it weren't in there like that, we should get -1. There are some others that we'll see, some other options. But what we're going to talk about in this section is how these are working behind the scenes and how we can implement our own versions of some of these functions, these built-in methods, and how we can search across arrays and strings. Or one more really quick example, if we had a list of states, an array in the US, I apologize for being America-centric in this video, but if this is what we had, we wanted to make sure a user was inputting a valid state. Well, we could check it against this, but how are we going to do that? What's the best algorithm? We're going to get into that in this section. So what are our objectives? First, just describe what a searching algorithm is. We kind of talked about that a bit. Then we're going to implement linear search on arrays. Then we're going to talk about a slightly better algorithm, binary search, on sorted arrays. So we'll talk about the pros and cons of those approaches. Then we'll implement a naive string searching algorithm, as well as something called the KMP string searching algorithm. So this section is really the first where we're getting into named algorithms. In the recursion section, for example, we talked about how to write a solution to the factorial problem, but it didn't have a name. Like, we haven't really seen code that has a particular name to the solution, but that's going to change in this section. And that will be something that we see throughout the course as a recurring theme. We'll talk about sorting. There's particular names for a lot of common sorting algorithms. So those are our goals. And the first thing we're going to do in the next video is implement linear search. All right, so we introduced the fact that we're talking about searching. For now, we're going to focus on searching an array. So imagine we have this array with states in it, which I didn't type this myself, just to be clear, I copied this. And so it also includes, I think there's 59 items. It includes territories like American Samoa, Puerto Rico's in here, Guam, things like that. But that's beside the point. So imagine that a user types something in and they're trying to, create an address, and they need to enter a state or territory. And for our application, we want to make sure it's in this array. What's the best way of doing that? And the simplest way is just to look at every single element in order and check if it's what we want, right? So if the user enters, let's say, Indiana, we would just start at the beginning and check, okay, is this Indiana? Nope. Is this Indiana? Is this Indiana? Is this Indiana? And we keep going until we get to Indiana, And in that case, we return something, true, or we say the index that we found it at. Or if it's not in there, we keep going until the end. And then we have some logic at the end that says if it's not found, return false or return -1 or something like that. Now that approach is actually not a bad approach. Now in this situation where we have sorted data, alphabetically sorted, there are better ways. But let's go back to, I think I had a list called usernames. This is unsorted. So there is no order to this at all. Now somebody enters, I hate cats as their username. How do we check if it's taken or not? In that case, the best way of doing it is to check every single element one at a time. Are you, I hate cats? No. Next. Are you, I hate cats? Nope. Keep going until we find it or we get to the end. Now that is called linear search. And in fact, JavaScript is doing that. Things like index of, which we talked about, includes find index. All of these methods are doing the same thing behind the scenes. They're checking every element one at a time to check if whatever we pass in. So let's do index of. Let's do usernames.index of Tommy. Index of 0. Let's do index of Q, which is towards the end, 15. We do index of something that's not in there, -1. We could also do the same thing with includes. I'm not going to go through all these methods, but let's try, does it include Tom? That's true. Does it include Toms? That's false. So what's happening here is that it is going through and checking each item to see, are you Toms, over and over until it hits the end. And if you looked at the source code, you would actually see the algorithm that we're going to talk about. And it's very straightforward. It's called linear search. So we've already been describing it. We visit one item at a time, starting at the beginning, moving forward, or we could start at the end and move backward. But it doesn't matter. All that matters is that we're moving at a set interval, one item at a time, checking every single thing. So if we were to have this list of numbers, this array, and we want to check for 12, we want to search if it's in there. We just start at the beginning. Is 5 12? Nope. Is 8 12? No. 1 is not 12. 100 is not 12. 12 is 12. And then we return true, or we return the index, 0, 1, 2, 3, 4. It depends on what we're doing. So for index of, for example, it would return 4. For it includes, it returns true. So that's linear search. And what I'm going to do now is something that is a bit different than how we've structured the course so far. I'm going to give you pseudocode to try and implement it. And I encourage you to write this code on your own. This is a nice and simple one. Here's the pseudocode. And then afterwards, we'll go through it and I'll write up the solution. So write a function, call it whatever you want, but it accepts an array and a value. So call it linear search, and it takes an array full of, let's just say it's numbers, but it doesn't matter really. Let's say it's numbers and then a value, another number. You just loop through the entire array and check if the current array element is equal to the value that we pass in. And if it is, return the index at which it's found. And if it's never found, return -1. Okay? So loop through the entire array, check for a value, whatever it is. Let's say we're looking for 3. If you find 3, return that index. If you don't, return -1. So this is possible in just a couple lines. Don't overthink it. Give it a shot. In the next video, I'll show you a potential solution. And keep in mind that even though this is simple, that doesn't make it bad. Like we discussed, it's used by built-in functions, things like index of, for example. Okay, see you in the next video. Okay, so in this video, I'm going to implement our basic linear search. So here's the pseudocode again. We're going to write a function. We'll call it, let's just call it index of, or linear search. And it's going to accept an array and a value. So we can start there. So I've made a snippet already called search linear. I'm having them all start with search, just like I did with recursion, so that they're just grouped together. So I made that over here, new snippet. I'm going to close that away now. And let's define our function called linear search. And it takes an array and a value. Let's do it like that. All right, so that's the first step. So I should be able to call it like this, linear search, pass in my array of, we'll just do numbers, 34, 56, 1, 2. And then the value I'm looking for is 1. And it should return the index, which is 0, 1, 2. It should return 2. So the next step is to just loop through the array and check if the current array element is equal to the value. So let's start by looping through the array. So that's going to be a for loop. Or, we could do a while loop if you wanted to. You could even just do a for each. There's many ways, but we'll do for var I equals 0. We're going to go from the beginning. So while I is less than array.length, add 1 to I. And then we need to check if the current array element is equal to the value. So we access the current array element with arr, array of I, and we're going to check if it's equal to the value. So we need to make this an if statement. And if that's the case, what are we going to do? We're going to return, well, we want to return, as you can see here, the index at which the element is found. So that's pretty easy because we already have I, which is why I chose not to use a for loop, or excuse me, a for each, although you can still do for each with an index, but we have I right out of the box because of our loop, so we just return I. So in this case, I will be 0, we start, we check, is array of I equal to the value? No. Is 34 1? Nope. Next up, I is 1. Is 56 1? Nope. Next time through, I is 2. So we check array of 2, which is 1. Is that equal to 1 that we're looking for? Yes. So we return I, which is 2. Then we have our final catch-all. If the value is never found, return -1. And the easiest way to do that is just after the loop. That means we've hit the end. So if we haven't returned by now, that means it's not in there. So we can just return -1, just like that. And a small simplification that we can make, we can do this all in a single line. The if statement, the conditional, just move that back up there, like that. Just shorten it a little bit, but it's just a personal preference. So if array of I is triple equal to value, return I. So now let's test this out. So linear search of this, we should, if it works, get 0, 1, 2. I'm going to use command enter to run it. And there we go, we get 2. Let's try it again. Let's add some other numbers. And let's check for 56. Which is actually, wow, I'm so bad at picking random numbers, I picked the same number twice. Let's change this one to be 51. And if I run it, we get index of 6, 0, 1, 2, 3, 4, 5, 6. Finally, let's test it on something that's not in there, like 100. We get -1. Now, if I still have my states array, there we go. Because I made this a snippet, I should be able to do linear search, pass in states, and then check what's the index of Texas, for example? And we get 50. And if I check for, let's do one more, how about Texas with an extra A? It's not in there. Cool. So this is linear search. This is what, behind the scenes, the built-in index of is doing. Any of these basic searches that we already talked about in JavaScript, what else was there? There was one, find index, index of, includes, all of those are using a linear search. And the last thing we should talk about is the big O of this. So take a moment and try and figure it out. The time complexity. As the length of that array grows, how does the time that it takes, the worst case, how much time does it take? And the answer is that it's O of n. So as our array gets longer, we have to do more searches. We have to do more operations. If we're searching for the last item, Wyoming, we might have to do 59, or we would have to do 59 searches. But if our states were instead 5,000 states, and we're searching for the last one, we would have to check 5,000 different items. So as n grows, as the length of the array grows, so does the amount of time. So this is O of n. It's linear, which is also, it's called linear search. Gave it away a little bit. And next, we're going to see another search that works differently, where if the data is sorted, as I hinted at, there's a better way of searching. And it's a little bit more complicated, but it's a fun sort of first algorithm to step things up a bit from linear search, and it's faster. So we'll see that in the next video. Welcome back. I've decided to make a separate video on Big O for linear search. I've actually already covered this content, but I realized some people were skipping through videos and not watching everything. So if I have a video titled Linear Search Big O, I found more people will actually watch that because it's really important stuff. Same thing for binary search after this. All right, so here's a quick video on how linear search performs, at least as far as time complexity is concerned. So best case, we have an array of 1,000,000 integers or 50 integers. The very best case is that we find the thing we're looking for right away. So that's the best possible scenario, right? But that's pretty rare, depending on the size of your data. The worst case is O of n. So if we have a million integers in an array and we're searching for the last one, or we're searching for something that's not in there, we're going to have to look a million times. If we have 50 things in there and it's the very last element that we're looking for, we're going to have to look 50 times. And average is also O of n. And you might think, well, isn't it actually less than O of n on average? Because sometimes we'll find it, right away. Sometimes we'll find it in the middle of the array, 2/3 of the way, 3/4 of the way. Shouldn't that average out somewhere? And the answer is no, not as far as big O is concerned. We care about just the general trend. So as n grows, as the length of the array grows, or the length of the string, whatever we're working with, so does the average amount of time it takes. Remember, we throw away all constants. So 2n, half n, 0.25n, those are constants. We ignore those and we just simplify it to O of n. Okay, so that's linear search. It's the best we can do with an unsorted piece of data. But next, we're going to talk about binary search, which is much better. And I'll have a separate video afterwards, once we learn how to implement it, on the big O of binary search and how we derive it. That's coming up. All right, welcome back. So we're moving on to our second searching algorithm. And this one can be a significant improvement on linear search that we saw in the last video. It's called binary search. So it can be much, much faster. We'll get into the specifics with big O later on, but it can be faster. Rather than eliminating one element at a time, like we did in linear search, where we checked one element, is this it? Nope. Is the next one it? Nope. Is the next one it? Over and over and over. In binary search, we can eliminate half of the remaining elements at any given point. However, there's a really big caveat here. Binary search only works on sorted arrays. So the data has to be sorted from, if it's numbers, lowest to highest, or highest to lowest, or strings, alphabetical, there has to be an order to it. So imagine we have our same states array. You don't have to imagine because it's right here. And this is sorted alphabetically. So you can see Alabama down to Wyoming. And let's say that we're doing the same example where we ask a user to enter a state and for their address or something, and we're going to verify that it exists in this array. Now, first of all, this is a very short array in the grand scheme of things, so linear search isn't really going to be it's not going to take much time, and the milliseconds, probably less than a millisecond. The tiniest fraction of a second that we're saving with binary search isn't really worth it. But since it's already sorted, it's a good example. Let's say that someone enters Oregon as their state, so in quotes, and we want to check if that's in here. Well, since it's sorted alphabetically, the way that binary search works is that we pick a halfway point in this array. So somewhere, and I'm not going to count exactly, I think there's 59. I'm not going to count the exact halfway point, but let's just guess roughly. Let's say that we pick states of, I think 29, it's 29.5, right? So we'll round down. So we pick our first spot, we pick the middle because we know it's sorted, in this case alphabetically. So the middle should be the middle sorted element. And then all we do is we check. So we find Missouri, there you are, and we check, is Oregon greater than Missouri or less than? In our case, alphabetically, is it after M, Missouri? Is it after that in the alphabet, or is it before? And it's after. So now we only care about this part of the array. We've just eliminated all of this. We don't care about the beginning. And we check halfway through the next little bit. And I'm just going to eyeball it rather than doing the math. But let's say halfway through is around 44. So let's say check states 44. That gives us Pennsylvania. So now this is the middle of this array here. And we go to Pennsylvania and we check, is Oregon before or after Pennsylvania? And it's before. So now we care about this list. From Missouri to Pennsylvania, we know that it's somewhere in here. We eliminated all of this here. So now we're going from Missouri to Pennsylvania, and we pick the halfway point again. And I think this is 16 or so. So let's go to the eighth one. 3, 4, 5, 6, 7, 8. So we go to New York, and we check, is Oregon greater or less than New York? And it's greater, so it's between New York and Pennsylvania. So we pick somewhere in the middle between New York and Pennsylvania. Let's say that it's Ohio. And we know that it's greater than Ohio, so it's somewhere between Ohio and Pennsylvania. We pick the middle, and now it's Oregon. And I know that seemed like a lot of work, but remember that was only, 5 or 6 guesses compared to if we started at the beginning with a linear search. We check this. Is this Oregon? Nope. Is this Oregon? Nope. Over and over and over. So it saves a lot of time if your data is sorted. So let's get down to the details of the implementation. So the idea is dividing and conquering. So we split up the array into 2 pieces. We pick a pivot point in the middle usually, and we check the left side and the right side and see where, based off of what we're looking for, where it will be in which half. So let's search for 15 in this list. Remember, it has to be sorted. This doesn't work at all if it's not sorted. So if it's sorted here, we're going to start by picking, we're going to call them left and right. So we're going to change the window of where we're searching, because remember, we can throw out half of the array roughly every time. So we're going to start with left at 1 and right at the end, 19. And then we're going to pick somewhere in the middle, and I think this is an odd number, so you can round down or round up, just be consistent as far as where you pick. So I think we're going to pick 11 here. I know we're picking 11. And we check, is 15 greater than 11 or less than 11? And it's greater than. So now we eliminate all of that to the left, and we make the new left 12. And the new right is the same, it's 19. Now we check somewhere in the middle. So we're going to check 17 as our middle point. And we check, is 15 greater than or less than 17? Is it on the right side or the left side? And it's on the left side. So we can eliminate 17, 18, 19. And now we have a left at 12, a right at 16, and then the middle is 15, which is our only choice. And we check, is 15 equal to 15? Is it greater than or less than? And it's equal. So we found it. So that only took 3 checks, 3 guesses. We checked at the middle first, 11, and we knew it was greater. So we did a second check. We picked 17, that was too big. And then we picked 15, and that was correct. Compared to starting at the beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9 guesses using linear search. So if we have a sorted array, numbers or strings or whatever it is, as long as we can compare easily to check if something is greater than or less than in some respect, if we can do that, then we can implement binary search, which is much faster. All right, so let's get on with the details of the implementation. Like I did in the last video or 2 videos ago for linear search, I'm going to give you some rough pseudocode, some kind of bullet points that you can follow, and you can fill in the blanks. It's not going to be a line-by-line guide to what you need to do, but it should set you on the right track. And if you have the time, the energy, the willpower to do it, to actually write it out yourself, I highly recommend it. It's not terribly long. It's maybe 8 lines, definitely less than 10, and 2 of those are just the function definition anyway, so it's pretty short and definitely worth your time. So write a function, we'll call it binary search, and it accepts a sorted array. Remember, we have to assume that it's sorted and a value that you're looking for. And let's also assume we're only working with numbers for now. Then you need to create 2 variables. One that's going to point to the index that the left that we're starting at, so 0 for our left arrow, our left pointer, and then a right pointer at the far other end of the array, the end. So that's going to be whatever the length is, -1. So we'll have left is 0, and then right is 10 or 1000 or whatever the end of the array is. Then roughly what you're going to do, you're going to loop over and over, and there's 2 things that you're checking for. One is, have you found the element? So while you haven't found the element, keep looping. But along with that, there's a second condition, which is you want to make sure that you're only looping while the left comes before the right pointer. And then you're also going to pick the middle. And you can just take an average of the left and the right, not the values, remember, but the position. So if left starts at 0 and right starts at 10, then you could take the middle to be 5. And then you're basically going to loop, and you're going to check, first of all, is the element equal to the middle? Is the middle what we're looking for? If it is, then just return, we're done. So if you find that value, return the index. If the value is too small, then you're going to move the left pointer up. And if the value is too large, you move the right pointer down. And then finally, at the end, if you never find the value, just return -1. Okay, so there is some flexibility in your implementation. There's a couple things that I didn't mention here that we'll talk about in the next video, like small changes we could make. But this is a rough outline. You pick a left, you pick a right, you pick a middle, and then you loop. And you basically keep looping while you haven't found, while the middle is not the answer. Then you're going to check if your value is less than or greater than the middle. And then depending on that, you reassign the left or the right, and you pick a new middle. So in the next video, I'll have a solution walkthrough. Hey, welcome back. So let's get on to implementing our own version of binary search. So again, here's the pseudocode. First, I just need to make a spot to actually write the code. So I've already done that. I'm doing it as a snippet again. I'm calling mine search binary. It really doesn't matter. if I were you, I'd probably do this in a file somewhere, save it on your computer, but this is easier for me. So I'm going to define our function. All that we said was that it needs to accept a sorted array and a value. So I'll just call mine binary search. Hopefully this is large enough. Let's see, shrink some of this down. Okay. Binary search takes in an array. We'll just call it ARR. And then the value, I'll call it element or LM. So for example, we should be able to call it with, let's do something relatively short, 2, 5, 6, 9, 13, 15. Almost all odd numbers. So let's do 28. Okay. And then let's say that we're looking for 15 in there. All right. So right now that's obviously not going to work. Next, we need to set our left and right and middle pointers, or I'm going to call them, I kind of prefer start and end and middle. And what we want to do is set the start to be here, the very beginning. Every time we don't want to exclude any of the array. So we always want to start at the beginning. So that's easy. Just make a variable, call it start equals index of 0. Then I'm going to make end. And end is going to be the length of the array, but we need to do -1. Otherwise, we're going to be out of bounds. So we want this index, which is it 6? 0, 1, 2, 3, 4, 5, 6. Yes. So 0 and 6. And then we need to take the middle. And this is just to begin. And the middle is just the average of those two. So in this case, 0 and 6, the average is going to be 3. 0, 1, 2, 3. So that's going to give us this position 3. But if we had one more item in here, like 30, then that throws everything off. So if I just had start plus end, and I need to add parens to do the average. Otherwise, it will just be start plus end divided by 2. This case, it's the actual average of them. But if we take a look, we're going from 0 up until 7 now. The average is 3.5. There's no index of 3.5. 0, 1, 2, 3. It's going to be right in between 9 and 13. That's not going to work for us. So that's where I'm going to do math.floor of that whole thing. You could also round up if you wanted to. You just need to be consistent in what you pick. Okay, so at this point, this is what we're looking at with this exact array. We start is going to be set to index of 0, which is right here. Then we have end is set to index of 7 in our case, which is now 30. And then the middle is going to be index of 3.5 rounded down, which gives us 3, 0, 1, 2, 3. So we have 9. And just to verify, we could do a console.log, start, middle, end, like that. And if we execute this, did I get anything? There we go, 0, 3, 7. So that's what we expect. Now we get into the actual logic. Well, what we want to do here, we want to continue to loop and repeat this process where we select a middle. Well, first we need to check if the middle is correct, right? Right off the bat, we could have picked 15. We didn't. We're working with 9. But let's say we were looking for 9. We picked the middle of 9 right away, so we need to check if we got it right. And if we didn't, are we greater or less than? Are we looking, is 9 too big or is 9 too small? In which case, we need to start searching over here only, or start searching only over here only. So let's start with just the simple while loop. So I'm just going to loop over and over while the element, or while array middle is not equal to what we're looking for. So while the middle is wrong, let's put it that way. So this first time, middle is 9. That's not what we're looking for. We want 15. So we're going to repeat this code. Now the code that we're going to do, first we're going to check. We can assume if we're in here, that means that the middle is either greater than or less than. If the number we're looking for is less than the middle, so if our middle is 9, let's say we're looking for 6. 6 is less than 9. So what we want to do is shift our end down to 6 now. Now you might think we could shift the end to 9, and that would work, but it's redundant because we know that 9 is not the answer already. We checked it. So we're going to set the end to be middle minus 1. So this is our new window. Likewise, the other direction, like in this case with 15, we check 9, that's too small. So we're going to move our window all the way up to here. So our start is now 13, and our middle is going to be 15 or 28. We'll round down, so it will be 15. So we want to do middle plus 1, or middle minus 1, because we've already tested the middle. So let's do that now. I'm going to have a simple if statement. If the element is less than array of middle, like that. If that's the case, like if we're looking for 6, we're going to set the end. We're moving the end down to here, right? So end equals middle minus 1. And then we have else. There's only one other choice, because if it's equal, if we actually got it right, then we're out of the loop. But we haven't gotten it right, so we're either greater than or less than. So else, that means that what we're looking for, in this case 15, is greater than 9. We need to move the start of our window to 13. So start equals middle plus 1, just like that. Then the only other thing, well, this isn't the only thing, but another thing we need to do is now change our middle value. We just need to recalculate it. So our first time through, let me just copy this. This is what we started with, and then we checked it. So array middle is not equal to element, right? 9 is not equal to 15. So is the element less than array middle? Nope. So skip this. Else start equals middle plus 1. So middle plus 1 is 13. So that means that our start is now 13 here. Our end is still 30. It hasn't moved. But we need to recalculate the middle. So we need to average 13 and 30. Well, not 13 and 30. We need to average those indices, which is going to be, what are we at? 0, 1, 2, 3, 4, and 7. So I'm just going to copy this exact same line without the var in that loop. We just get a new middle. So now middle is going to be math.floor of 4 and 7. So that's what, 11 divided by 2. Floored is going to give us 5, index of 5, which is this item here. So this will be our new middle. And just to verify that, let's move this line into the loop so that we see what we get each time through. Okay, so I'm going to run this now. Let me clear my console. Make this a little bit bigger. Okay. And, oh, it looks like it's only running once because at the end, we got the answer correct. So I picked the example of 15 was too easy, but you'll see at the end, it's 0, 3, 7. So that's what we have, 0, 3, and 7 indices. Then it updates to go from 4 to 7, which is what we have here. And the middle is 5. And what do you know? That's what we're looking for, 15. So we broke out of the loop because array middle is now equal to the element. Now if I pick something else, let's say I pick 28 this time, we'll get an extra step. Execute it again. There we go. 0, 3, 7, same thing. But this time 28 is greater than 9. So our window now is from here to here. And the middle is 15, which is what we checked. And that's too small. So then we have another iteration. And in this case, it's too small. So what do? We shift the start up again. Let me get rid of the M. And the start now goes to 28 here. Our end is 30. And our middle, when we take the average, we're going to round down. So our middle is also here. So it looks more like this. And that now means that we've guessed the number correctly because our middle is 28. And you can see that our middle is index of 6, our start is index of 6, our end is index of 7. We've found it. So at the end, what we should be doing, for now at least, is just return middle. And if we test this all out, we're returning 6, index of 6, and that's correct when we're looking for 28. If we're looking for 5, we're returning index of 1. That's correct. There's a big problem with our code though. And the problem is if the number isn't found in there, our code doesn't handle it. And I'm not going to do this. I recorded this video once before, and I actually showed what happens. There's an infinite loop going on. Hopefully, we'll see if you can spot why. But let's say I'm looking for 50 in here. We're not going to find 50. Our code doesn't handle it. And the browser just keeps looping over and over and over. And with my recording software, plus the browser doing that, my computer was really not happy, and it got like 1,000 degrees. So I'm not going to replicate it here. But what would happen is that we would get basically thousands and thousands. Eventually, it would be shut off, but tens of thousands of iterations, if not more, because we're never going to find that element. And the only way our loop ever stops is when we find it. If our middle index is equal to the element, we break out. But our middle index is never going to be equal to, or the item at the middle index is never equal to 50 or 1 or 14 or any number that's not in here. This is going to go forever. So what's our other stopping condition? Well, if we look at what happens, as we approach a number that's not in there, we do the same thing, right? 2 is our start, or 0 is our index. This is our end, 7, and this is our middle at index 3. Well, we check 50 is greater than 9. So we move the window up to here, as you see there. So now our start is 13, or index of 4 up to 7. We take the middle, index of 5, and 50 is still greater than 15. So now we move up again, and this is our new window. And our middle is 28. And we check, is 50 greater than 28? It is. So what's our final iteration going to look like here, or what should it look like, is that we're going to move the start to be middle plus 1, which is 30. So then we end up with everything, start, middle, and end, all at 30. We've hit the end of the list. So then what's next? Because our code is still saying, all right, well, the middle is 30. We're looking for 50. So we need to move the start to go up 1. And there isn't anything after that, but it's going to increment our start, or it will increment our start to be 8 at that point, which is out of bounds. So then if we tried to do that array of 8, we're going to get undefined, and then we're going to start comparing things with undefined, and it's just not good, and it's going to keep going forever and ever. So we don't want that. Okay, fine. I am going to show it to you what happens, and my computer's not going to be happy. Here we go. As you can see, it just keeps going and going over and over, and it sets the start now is 8. Okay, I'm back. After my computer's not very happy with me, but it worked out. So what happens at the end is that our start, middle, and end converge, and then our start gets above. Our start is set to be middle plus 1. So the next time through, if we're working with the start is 8, the middle is 7, and the end is 7, if we go through again, we're checking is the array middle, which is still 7 because we take the average of these, 8 and 7, and you floor it, and you're still stuck with 7. So our middle is not going to budge, and it stays at 7. And then we go through again. Is element less than array middle? No, it's greater than, because we're looking for 50. So 50 is greater than, so we get start equals middle plus 1. So start is 7 plus 1. So we're not moving anything, and we get stuck because we've hit the end, basically, and we've crossed over, if that makes sense. Our start has eclipsed our end, and it's stuck that way. We're going to continually set this to be 8, the start will be 8, the middle will be 7, and it just keeps going over and over and over. So we want to stop. We want to make sure this loop only runs while our start is less than or equal to the end. So as soon as the start becomes greater or the end becomes less than, we have a problem. So just in here, I'm going to do and then we just check start is less than or equal to end, just like that. Okay. So we're close now, and if I run this time, we still have a problem, which is that we're returning the middle, even if we don't find it. So now we don't loop forever, but it's returning index of 7 because that's where we stopped, right? That's our last point right here. So index of 7, but that doesn't work because 50 clearly is not at index of 7. So now we just need to add a little check at the end. We want to check basically if array of middle is equal to what we're looking for. Oops. Like that. If it is, then we return middle. Else, what do we want to return? We'll return -1, I think is what we said, right? Yes, it is. Does that make sense? So we're checking if the array middle, the item at the middle index is what we're looking for. Should do triple equals. We'll return middle. Otherwise, return -1. So now we get -1. But if we search for 5, it gives us 1. If we search for 9, it gives us 3. If we search for -1, we get -1. -10, still -1. Okay, so a couple small cleanup things we could do if we wanted to. We can, well, first get rid of the console.logs. We don't need that. Next, we can condense some of these conditional statements. So I'm going to duplicate the solution because some people like to have a longer version, but I will also do a shorter version where we get rid of basically a lot of white space like this. So do a single line if statement, And then our else doesn't need brackets either. So there's one reduction of a couple lines. And then we can also put all of this on a single line using the ternary operator. So that looks like this. Or there's two implementations. So we can just do return array middle equals element. If that's true, so we need this question mark, we're going to return middle, colon, else return -1. If you haven't seen that syntax, the way you would read this is return the result of this whole thing, first of all. And the result is going to depend on if array of middle is equal to the element. So if array of middle is equal to element, return middle. Else, return -1. So just test it out again. It looks like it's working. Let's plug in a number that is in there, like 30, and we get index of 7. If we plug in 13, we get index of 4. If we plug in 103, we get -1. Okay, so that's our shorter solution. All that we did, the logic's the same. We just got rid of some of the extra brackets and the longer if statements. So we made it through there. Hopefully it makes sense how this all works. And now we're moving on to a couple other searching algorithms. So keep in mind this works great on a sorted array. Otherwise it's useless. So linear is the best that we can do. What we saw a couple videos ago is the best we can do on an unsorted array. Binary, though, works great if our data is sorted. All right, welcome back. So I'd like to talk about the time complexity for binary search, how it performs, let's just say, on an array. So as the length of the array grows, a sorted array, of course, how does the time complexity grow in relation? And you can see here on the left, worst and average case are O of log n. And I'll come back to that and why that is. Best case, of course, is O of 1, because it's possible that the very first thing we pick is the element we're looking for. If we pick the middle point of an array and that's what we want, well, that's one operation, it's constant time O of 1. That's pretty rare, but it's possible. Worst and average case are both O of log n, and I have a couple slides to detail how we get log n. If you're not familiar with logarithms and how this applies to big O, I have a quick video. I think it's the last video of the big O section. I definitely recommend you watch it if you're not sure about logarithms, if you were taught them a long time ago and you forgot them, or if you were never taught them. It's a quick video. So suppose we're searching for the number 13 in this array. How many steps does it take? Well, we actually can see 13 is not in here as a human. It should be right here if it were to be in this array. But the first step is to pick a midpoint. And I know this looks like it's not the middle, but these are all double-digit numbers over here, so it's kind of skewed. But this is the midpoint. So we pick 19, and we check, is 13 less than or greater than 19? It's less than, so we know it's somewhere over here if it's going to be in here. So then that's what this array is representing. We're not actually shrinking the array down, we're just looking at this portion of the larger array. So then we pick a midpoint again, which is 9. Well, 13, is that less than or greater than? It's greater than 9. So we're now looking at this subarray, 11, 14, 15. So we pick the midpoint 14. Is 13 less than or greater than? It is less than. So we're looking at this subarray now, 11. So we check, is 13 equal to 11? The answer is no, of course. And so we know that 13 is not in this array, unless it's somehow an unsorted array, in which case we shouldn't be using binary search. But given the conditions of binary search, we can say without a doubt 13 is not in this array. Nope, not here. So if we look at the number of steps here, we had 16 elements. It took 4 steps to say with certainty that an element is not in there. So we could have found it earlier if it actually was in this array. If we were looking for 9, for example, it takes 2 steps. If we're looking for 14, it would take 3 steps. But if we're looking for something that's not in there, or the very worst case, it took 4 steps. Now, 16 elements, 4 steps. Let's grow our array. Let's double it in size. So instead of 16, I'm adding 16 more elements. So we have 32 elements in our array. It looks like this. And let's say I'm looking for the number 32. How many steps will it take? Well, in the first step, we pick a midpoint. This is not counting as a step. This is just our starting array. I pick the midpoint, which is 16. And we test, is 32 greater than or less than 16? It's greater than. So we can ignore all of this. There we go. This slide took a long time to make. So now we're looking at this part of the array. And we pick a midpoint, which is 24. And we compare 32. Well, 32 is greater, so we can ignore all of this. Next, we're looking at this portion. and we pick a midpoint again. 32 is greater than 28, so we ignore all of this. Skip. Now we're looking at 30. Well, we're looking at this portion, and we pick a midpoint, which is 30, and 32 is greater than 30, so we ignore this portion. Finally, we pick our midpoint again, and we find 32. We're good to go, and that took 5 steps. 1 step, 2, 3, what? It's highlighting the wrong thing. 1, 2, 3, 4, 5, until we found it. So we doubled the number of elements from the previous slide. We had 16 elements, which was 4 steps to find, or actually we didn't find the element, but it took maximum 4 steps. Here, we doubled it to 32 elements, and it took a maximum of 5 steps to find our element. So that relationship is log base 2 of n. So log base 2, which we simplified to log n, basically means 2 to what power gives us n. So if we go all the way back here, 16 elements, what is log base 2 of 16? It is 4, because 2 to the 4th power gives us 16. 2 times 2 times 2 times 2. Or here, it was log base 2 of 32 elements. If n is 32, that means 5. 2 times 2 times 2 times 2 times 2. So every time we double the size of n, every time we double it, we are simply adding 1 extra step. So log n is really good. If we look at the big O complexity cheat sheet little graph here, you can see log n is all the way down here. It's really good. It's so good, in fact, they don't even put a separate line in here. So there's the O of n line, our linear big O. And then down here, they put constant and log n together, because in the grand scheme of things, when you zoom out far enough so that you're looking at something that also includes factorial, O of log n is so much better that it just looks like O of 1. Anyway, so log n is really good. Binary search is very fast. Of course, the caveat is that it only works on a sorted array, and if you don't have sorted data, then you're out of luck, and you've got to use linear search, which is not anywhere near as good. Going forward, we actually will see a couple other algorithms when we talk about things like binary trees and graphs, where the big O notation for time complexity includes log n again, or also n log n. So if you're not comfortable with logs yet, I really recommend you watch that video, but also give it some time. I think we have a couple sections before we encounter log n again, but soon we will. Hey, welcome back. So we're still talking about searching algorithms, but now we're talking about a different type, which has to do with searching for substrings in a larger string. So there are 2 that we're going to focus on, and the first one is the naive string search. I don't think there's actually a name for this. This is just the most basic, common way of doing this problem, and then we're going to see a better implementation that is definitely a little more complicated in the next 2 videos from now. But we're going to start with the basic solution. So imagine that you want to count the number of times a smaller string appears in a longer string. A straightforward approach involves checking pairs of characters individually. So imagine we have this string here. Harold said, haha, in Hamburg. So if we were searching for just a single character, like, I don't know, the letter I, for example, that's very easy. That's basically what we've done. You just do a linear search. You could treat this as an array, right? You just check, is this an I? Nope. Is this an I? Is this an I? Is this an I? Over and over until you find an I or until you hit the end. So that's nothing new. If we're searching for a single character, we can use what we've already done. Instead of accessing items in an array, we access using an index in the string, just like this, right? 0, and then we check 1, and then we check 2. But if we're checking for a pattern, for example, I want to see if HA, haha, is in there. That takes some more work, because we're no longer just checking a single character against a single character. We're checking, okay, let's walk through the string, and it looks like we have an H, so that's a match, and then we have an A, oh, that's a match, and then an R, oh, not a match anymore. So then we start over, and we look for an H again. So I actually have a little diagram here. Imagine that this is our long string we're searching through, and we're trying to find OMG inside of this. So the simplest approach is going to involve, basically, if we put them next to one another, we're going to start by walking one character at a time. And we're just going to check, is this W here equal to the O at the beginning? Are these 2 characters the same? No. Okay, move on. Now we have a match. O is O. So now we move on to the second character. We're looking for an M. We don't find one. So we move on. W and O, we don't find that, so we move on again. Okay, O and O, that's a match. Now we move on to the next character, M and M. That's good. G and G, and we hit the end of our short string, we found a match. So now we add a count, or we increment something to keep track of how many matches we found. We found 1 so far. Now we move on to the M. So basically we do it for every single character here. And we start at the beginning of our smaller string and check it against every individual character in the longer string. So that's not a match, that's not a match, that's not a match. Now we have a match at the O, so then we check the next character. M, we check, there's still a match. G, and we increment. I don't know why when I made this slide, I just checked, these are the same size. Somehow there's some weird bug when it's being displayed. But these should count evenly. There's 2 matches. And that's what we want to do. We want to try and implement this naive string search. So there is a better way of doing this, but it involves a lot more code that we'll see in 2 videos from now. And it has a much fancier name. But this approach is one that it just takes a couple lines, a couple loops. Let's walk through the pseudocode. So the idea, again, is for you to try and implement this on your own using the pseudocode if you have the time or willpower or energy. Here's the steps. So loop over the longer string. So I guess I didn't say define a function this time, but define a function that takes 2 strings and just call it maybe string search. It takes the larger string and then the pattern that we're looking for. And then you loop over each character in the longer string, and then we have another loop over the shorter string. And then we just check. Basically, if the characters don't match, break out of the inner loop, so stop. And if they do match, if we find a match for O, for example, in OMG, then you move on to the next character. Keep going until you hit the end of the short string. And if you do hit the end of that short string, that means that you found a match. So if you complete the inner loop, find a match, increment the count of matches, and then return the count at the end. And so if count should start at 0, we don't need to have any special error handling. If there are no matches, count stays at 0. So just return the count at the end. So hopefully that makes sense. Loop over the longer string, inside of that loop, a nested loop over the shorter string. And then if you make it to the end of that shorter string and you haven't broken out yet, then add 1 to the counter. Okay, so give it a shot. In the next video, we'll have a solution. All right, welcome back. So in this video, we'll go ahead and implement the naive string search algorithm. So I already have a snippet created. Do this wherever you prefer, Sublime, some text editor, as a snippet yourself. It doesn't matter. So I have one called search naive string, and I'll close that for now. First, let's just define the function. So it needs to accept 2 strings. So I'm going to call it naive search, and it accepts the long string and a short string, or long and pattern. I've also seen that, or pattern like that. I like short though. And then the first thing that we'll do is just do a sample call down here. So naive search, and let's say, for example, that we would be calling it with maybe Lori lolled, LOL'd as a verb, and we're searching for LOL in that string. Okay, so first of all, we're going to need to get some loops going, as the pseudocode mentions. Loop over the longer string, and then nested inside, loop over the shorter string. So let's just start with the most basic loop over the long string. So for var I equals 0, while I is less than long.length, I plus plus. So that should give us every I, if we just look at it. I'll execute this, make our console a bit bigger. Come on. All right, so we get 0 to 10. There's 11 characters in there. Then let's do the same thing, this time for J, or whatever letter you prefer, but J is the standard one, H-I-J-K, yes, yeah. Okay, for var J equals 0, J this time is less than short dot length, J plus plus. It gets a little confusing once you start working with I and J, keeping track of which one is which. So if we just printed out I comma J each time through, those are going to be numbers. So why don't we do instead, let's do long of I, so we see which character we'd be referencing, and short of J. Now we're going to get a lot of prints. This is a nested loop, so we're looping 10 times here, but each of those 10 times we're looping 3 times for the LOL. So if I clear this out, I'll make this larger and try it again. All right, so you can see what we get here is basically we start with L on both of them, L and L. And then the inner loop goes to O. So we have L and O, and then L and L again. And then we move to O. and we start over. O and L, O and O, O and L. Okay, so what do we actually want to do rather than just printing them out? Well, the first thing that we can do, let's forget the fact that I and J are numbers. And let's just say that they're the letters exactly. It's a little easier to talk about. So let's say that I starts as L and J also starts as L. So remember that I is our outer loop. So I is going to stay L as we progress through LOL, if that makes sense. As J increases, it has to increase 3 times and then reset in order for I to increase once. So we start the loop. I is L, J is L. We compare them, looks good. Whenever there isn't a match, we break out of this inner loop and we move on to the next iteration. But let's just focus on, in this case, there is a match, L and L. So what do we do next? Well, the next comparison is still going to be L, but it's going to be compared to O because we're moving, basically J moves on and it becomes O because we're looping through this first. But that's not going to work to directly compare O and L because we know that's not a match. So what we want to compare it to is one more than L. So as we move through J, we want to also look ahead in I, even though I is going to be stuck at 0, if that makes sense. As we look through this, as our short pattern, LOL, continues to loop, we're still comparing to L each time. So instead, we want to look ahead. And the best way to do that, or one way at least that I'm going to do it, is by adding I to J. It's kind of confusing. But now if we go back to numbers and we say they both start at 0. Okay, so there's a match. Now J goes up to 1. So we're going to compare LOL of 1, which is O, to this string, Lori lolled, but instead of 0, we're going to add them together. So where we were before plus where we are now in J, which means that we're going to look ahead to O because that would be index of 1. And so that's a match. Next time through our short string, we're at index of 2. So we're going to compare this L and we are going to add 0 plus 2 to give us index of 2 of this string, looking ahead, and it's not a match. So then we break out. That means that we start again at L. But then once we get up to here, which is what? Index of 0, 1, 2, 3, 4, 5, index of 6. So in the scenario where we are here, index of 6 in the large string, index of 0 in the short string, there's a match, right? Those are matches. So then we move on. In the short string, J goes up by 1, and it now becomes 1. But we don't want to compare Lori lolled of index 6. We want Lori lolled of index 7. We add them together. So hopefully you can see the approach. We're looking ahead. And to do that, it's not too bad. All we do is add I and J together and access, using that new index, access the long string. So here's my approach. Instead of console.logging, we'll just basically check if the short string of J is not equal to the long string of I plus J. Now, if that happens, then we'll break out. So let's make this a loop. A conditional. Like this. So this means break out of this short loop and start on J again at 0. So anytime there isn't a match, we're going to break. So if I add this console.log in there now, where I'm printing short J and long I plus J, I'm going to clear out like this, and let's see what we get. Okay, so our comparisons. We start with L and L. That makes sense. There's a match. So we don't break out, and we move on to O, and we compare O to the next character, which is O. And then there's a match. So we move on again to L, and we compare it to R, in which case there wasn't a match. So if I added in a console.log here to say break and reran this, you can see what happens. So it looks like there's a match, L and L, O and O, and then there isn't a match, so we break. And when we break, what is happening there is that J is being reset. This inner loop is going back to 0, meaning we start at L again. But the outer loop, I, moves on. So now we're starting here at O. So after that break, we do L and O, and that's not a match, so that's a break. So then we move forward again. This time, we're talking about R and L, and that's not a match, so we break. We keep going until finally we get here. And there's a match, so then we move on. And there's another match and another match. But what do we not have right now? We're not actually incrementing any sort of counter when we find a full match. So we found a full match right here, LOL. Those are three pairs that match correctly. So what we need to do is make a variable up here. Let's just call it count equals 0. Now, when should we increment count? Well, the way that we know that we have successfully made it through this string, because if we get to this last character and there's a match, if we've made it to that point, that means that J is going to be whatever the last character in the short string is, if that makes sense. So if we had LOL'd, L-O-L-E-D, we know that we've finished if J is 0, 1, 2, 3, 4, if J is 4, or in this case, if J is 2, if we've made it to that point. So we can just add a conditional check, just do an if, and then we just check if J is equal to the short string dot length, but -1 because the length is going to be greater than the index. If that's the case, let's add 1. Let's do plus plus like that. And then at the end, let's return count. Let's see, how many braces do I have? So that's conditional loop loop. Okay, here we go. Okay, so let's see what happens now. So why don't I add a console.log in here, found one. Clear my console, rerun the whole thing. Let's try that again. Okay, so if you see, we have the same exact thing, almost a match, but there's not, so we break, keep going. But then, hooray, we found a match, and so this code is printing. So count is going up by 1. So if you get this, if it works for you, or if you had a slightly different solution, but it's working, that's all that matters. If you have 2 loops and you're getting it to work, your logic can be slightly different. You could work from the end, for example. You don't have to work from the beginning forward. You could work backwards. That doesn't really matter. But if you have it working, great. If you want, you can stick around and we can walk through this one more time just to see exactly how it works. I'm going to shorten this up because, like some of the other solutions, we can put these on single lines, make it a little nicer, like that. Same thing with our second if. Move that up here, just like that. And it still works. Should still work at least. We're getting it results printed. Come back, console. Yes, we're getting 1. Cool. All right, so if you want to stick around for the extra walkthrough, let's try it one more time with something different. Let's try it with LO, which in this case, we should get 2 matches. Is that working? Yes, we get 2. All right, so what's happening here? Well, we loop through every character. For example, L is where we start. And on the second string, we loop through every character. So we start at L. And immediately we check if this character doesn't match I plus J of this character. So I and J are both 0. So this means we're checking the first characters together. 0 plus 0 is 0. So if they don't match, immediately break out. And that means that we move on and that I is now right here. So if they do match though, which they happen to match, what do? Well, since we're still in this loop, we move on. J is now pointing to this, but I is still here. So now we add those 2 together. J is now 1, I is still 0, so that gives us a total of 1. And we compare this to that, and there's a match, at which point we increment count, because J is equal to the length of the short string. That's how we know we're on the last iteration. J, in this case, would be equal to 1, 0, 1. When we get to 1, and we haven't broken out yet, if we get to this point, that means we found a match. All right, so then it repeats again until it finds this match. So hopefully that's clear. And if we try it with something that isn't in there, like pop, we should just get 0. And we do. So we don't have to account for anything because we have this count variable. It's unlike binary search, for example, where we had to handle errors, not errors, but we had to handle those edge cases. If we don't find anything, we count 0. All right, so that is an implementation of naive string searching. Next, we're going to see a better implementation of a different sort of string search algorithm. Definitely a little more complicated and longer, but it'll be fun to talk about, I think.